So, Chloe's school is holding elections for 5 positions on next year's student council. And there's 5 students that are competing for 5 different positions. Okay. So 5 positions, 5 students. So how many different ways can Chloe fill out the ballot if she votes for all 5 positions? So if there's 5 positions, the first way that we learned it using the fundamental counting principle would be that there are 5 ways to fill the first position. Then once that person's chosen, there's 4 ways left, then 3, then 2, then 1. 20 times 3, 60 times 2, so 120. The way that we looked at it yesterday was using factorial notation. So that was just another way that we could represent this, and that's the same thing as saying 5 factorial. Right? Sorry, not 12, 120. Right? So that's the same as 5 factorial. So that factorial just means multiply descending natural numbers. So what we're going to do now is use a fundamental counting principle to look at what if she doesn't vote for all 5 positions? Like what if she only votes for 4 of them, or 3 of them, or 2 of them? And I want to stress that everything that we're doing today can be done using the fundamental counting principle with lines, or it can be done with the formula that I'm going to introduce. They both mean the same thing. So what I'm teaching you now is essentially the fundamental counting principle. We're just not always running down to there only being one choice at the end. What if she votes for only the president, vice president, treasurer, and secretary? So she only votes for 4 positions instead of 5. And there's still 5 people running, but now instead of voting for 5, she's only going to vote for 4. That doesn't change, right? 5 times 4 times 3 times 2, because the times 1 is redundant. It happens like at the end of it. So that doesn't change, because that last person by default gets the last position. If she only votes for 3 people, so president, vice president, treasurer, but there's still 5 people running, then she's got 5 choices for president, 4 choices for vice president, 3 choices for treasurer, the last 2 choices. So then that's 5 times 4 is 20 times 3, so that's 60. Or she might only vote for president and vice president. So there'd be 5 choices for president and 4 for vice president, which gives 20 different ways she can vote. And if she only votes for the president, and there's 5 ways she can vote, right? So if she only votes for president, she's got 5 people she can pick from. This means like there's 20 different ways. If she votes for president, vice president, out of 5 people, there's 20 ways of having a president, vice president in 2 different positions. Any questions about that so far? Okay, Natalie claims that the expression 5 factorial divided by 1 factorial represents a number of ways Chloe can fill in her ballot to vote for only the president, vice president, treasury, and secretary. So this one up here. She's saying that that's equal to, so that 5 times 4 times 3 times 2, which is 120, is the same as 5 factorial divided by 1 factorial. Now, without calculating that out, using some of the method that we used yesterday, right? 5 factorial is 5 times 4 times 3 times 2 times 1 factorial divided by 1 factorial, and those cancel out, okay, which ends up getting me the same as where I started. So I might be able to do the same. So when I've got 3 positions to fill, or I'm going to vote for 3 positions, she had 5 times 4 times 3, which was 60. But what if I do 5 factorial divided by 2 factorial? And I'm taking the total number of people there are, and I'm dividing out the number of people she's not voting for. So this would be 5 times 4 times 3 times 2 factorial divided by 2 factorial. And those cancel, and multiply them. So maybe they might work the same. 5 times 4, which was 20, would that be the same as 5 factorial over 3 factorial? Right? So 5 times 4 times 3 factorial divided by 3 factorial. So the thing is, though, is that notice that, can you see a way to get the 2 from this? Like if she's going to vote for, so this was where she was voting for 3 of the 5 positions. Like where does the 2 come from? So ones you don't want. Yeah. So that number on the bottom, okay, so in this case here, so if we look at this one, okay, we have 5 people, and she's voting for 3 positions. So there's 2 positions she's not voting for. Voting for 3 positions, not voting for 2 positions. So 5 factorial divided by 2 factorial is equal to the number of people on the ballot factorial divided by the number of people on the ballot minus the number she votes for. Factorial. Okay, she votes for 3, and so 5 minus 3 gives me 2. So there's 5 on the ballot, 5 minus 3 gives me 2 that she doesn't vote for. And that leads us to a formula for what we call a permutation. So suppose there are n positions on the student council and Chloe votes for R of those positions, okay? So n is the total number of people on the ballot, R is how many she's voting for. We want to write an expression that represents the number of ways she could fill out her ballot. So the top number was the number of people on the ballot, and the number on the bottom is the number of people on the ballot minus the number she's voting for. So suppose there are 10 student council positions, and she votes for only the president and vice president. We're going to use this expression, but I want to use the other ones first. If there's 10 people on the ballot, and she's only going to vote for a president and a vice president, there's 10 people on the ballot, so there's 10 choices for president and 9 choices for vice president, which gives me a total of 90. So I got to verify using the fundamental counting principle. I verified first. If I use the formula I have up here, then I get 10 factorial divided by 10 minus 2 factorial. Sorry. Minus 2 factorial. So that gives me 10 factorial divided by 10 minus 2 is 8 factorial. And then remembering back to how we were expanding and canceling yesterday, this gives us 10 times 9 times 8 factorial over 8 factorial, where those cancel. So what we have is 10 times 9, which is 90. So going the other way, what voting situation would the expression 10 factorial over divided by 10 minus 6 factorial represent? How many people on the ballot in this situation? 10. Okay, and how many did you vote for? 6. Yeah. So 10 people on the ballot. Vote for 6. So a permutation permutation, one of the first things about permutations that you need to know is, and it's probably the most important thing, its order is important. So what I mean by that is back, like if we were choosing a president and vice president from 10 people, okay? Let's say that Kaylee Kaylee is president and Aurora is vice president. Kaylee being president, Aurora being vice president is different than Aurora being president and Kaylee being vice president. That means order is important. If it was just a committee, 2 people on a committee, then Kaylee and Aurora is the same as Aurora and Kaylee. Okay? The way of thinking about a situation where order is never important is cards. Right? When you have a hand of cards, the order that you put them in when you're looking at them doesn't matter, which means that the order a hand is a hand, a 5-card hand is a 5-card hand, no matter how you have them organized. Everybody organizes a card system in different cards. So cards order isn't important, but a situation where there's specific positions to fill, order is important there. And a permutation is just an arrangement. So in math, a permutation is referred to as the number of arrangements of n objects taken R at a time. And the formula for that, and it's on your formula sheet, it's NPR. N permutation R, or what we always say is N pick R. Okay, and the N and the R are subscripts, they're down low. And what that means, if you see NPR, it means N factorial divided by N minus R factorial. Where R has to be greater than or equal to 0 and less than or equal to n. And you can't have any negative numbers. And what we were doing yesterday, like a special case, n pick n, is just n factorial divided by n minus n factorial. So n factorial over 0 factorial, which is just n factorial. 0 factorial. What you want to do in questions like this is figure out what n is and what r is. Now the thing is all of these questions can be answered using this formula or just using the fundamental counting principle. It depends on what you feel like using and what you feel like typing into your calculator. In terms of on your calculator, factorial is under math. Permutation is the same way, same place. So if you go to math, and then over to probability, permutation is number 2. So it's math probability. Please, sorry, let me clear that up. You have to put in n first. N, then pick math, then pick probability. Prob, not prop. Then it's 2. And then you put in R, and then enter. The only time you have to use the permutation formula is if you're solving for n or r. Okay, so if you have a question that was sort of like what we did at the beginning of class today, but where you're solving for n or r. That's the only time you have to use this formula. If you don't like using the formula and you just like drawing the lines, doing fundamental counting principle, that works the same. And so I'll show you both ways here. 8 actors are auditioning for a play with 4 roles. So roles in a play are specific, right? So that like the 8 actors, like it's a different cast if they're in different roles. So that means order is important. We want to know how many different cast lists are possible. So n is equal to 8. and r is equal to 4. So as a permutation, it's 8 pick 4, which is equal to 8 factorial divided by 8 minus 4 factorial, which is 8 factorial over 4 factorial. Or use your calculator. Like so you don't, like you can, like if we do this, this way we would tend to from here. If we're just doing 8 pick 4, I'm showing you that that's what that means. So let me actually kind of change this thing. That's what that actually means. 8 factorial over 8 minus 4 factorial, which gives you 8 factorial over 4 factorial. You don't need to write that out. What you want to do is just, you want to put that into your calculator. So if you push 8 on your calculator, so 8, then math, probability, 2, and then 4, you should get 1,680. So make sure you can do that on your calculator. A non-graphic calculator is a lot easier to use for firms at home because usually the keys are right there. So it's either right on the calculator or a second option. Sorry, I've got prob in there, but it's on mine. I think it's prob. On mine is karaoke. Okay. Now, the other way that you can do that, so that's using permutations. That's using the formula. If you don't want to use a formula, use a fundamental counting principle because you end up in the same place, and a lot of you will find this method easier. That's where you figure out, okay, there's 4 rows. I've got 4 lines. How many actors can I pick for the first roll? Well, that's 8. For the second roll is 7. For the third roll is 6. And for the fourth roll, as I can count, 5. And then you multiply those all together. So 8 times 7 times 6 times 5. Which is the same thing, 1680. And you should be able to recognize that 8 factorial divided by 4 factorial. So 8 factorial divided by 4 factorial, if we use the method we were using yesterday, 8 times 7 times 6 times 5 times 4 factorial divided by 4 factorial. That's what you end up with the same thing. Because it's essentially, it's just putting a formula on what we did yesterday. Okay, so you guys try the one on the bottom. Okay, there's 2 there. Determine how many possible, all the possible 7-song, 8-song, and 9-song playlists you can create from 10 songs. And it's more to practice using the key. This is maybe not one that you'd want to multiply out because you'd have 10 times 9 times 8 times 65 if you have quite a few to do. I inadvertently sort of already answered the next example, but we'll do it anyway. It's just using, we want to use the formula for n pick r to show that 0 factorial equals 1. So our formula, remember, is n pick r is equal to n factorial divided by n minus r factorial. And then on the previous page, like I mentioned, like n pick n, like that, is just equal to n factorial over n minus n factorial. Well, we know n factorial is just equal to n times n minus 1 times n minus 2 times n minus 3, and so on all the way down, 3 times 2 times 1. So then, when we end up here, n minus n factorial divided by 0 factorial, well, we know like that like if we're, sorry, what I'm trying to say is if we're going to, we've got n objects, we want to know the arrangements of n at a time. So like English, where we had 7 objects, we want 7-letter arrangement. 7 times 6 is 5, 4, 3 times 2 times 1. So that's what this stretch is here. So then that means that this would have to be, this has to be equal to n factorial, which implies that 0 factorial is equal to 1. I wouldn't worry too much about the justification for that. you just need to know this. You need to know 0 factorial is equal to 1. It's got nothing to do with exponents, but I always keep in my head anything raised to the power of 0 is equal to 1. It's the same idea here. So this thing, I've got this as your term, but I'm going to do this together because this one's a bit tough. Because what it means, like what this means, if 0 factorial is equal to 1, this is only valid, right, if like your values of n and r have to be greater than 0. So this, if this is anything less than 0, it's not defined. So that the smallest value this can be a 0. So if we figure out for that in that brackets what makes that expression equal to 0, so n equals -3 would make that equal to 0. So that means n has to be greater than -3. Greater than or equal to -3. It's a little bit like finding non-permissible values, but kind of the opposite thing. Like you're just basically to figure out the values for which a factorial or a permutation expression is defined, you have to figure out what values of n make the expression equal to 0. So for this one over here, right, n factorial, n equal to 0, so n would have to be greater than or equal to 0 for the top one to be defined. N plus 2 factorial, n plus 2 equals 0, so n equals -2, so n has to be greater than or equal to -2 in order for the bottom one to be defined. So you pick the higher one, right, because -2 would make the top one not defined, so that would be the restrictions that would be on this particular Okay, so now we'll just do some more examples, and I'm trying to show you how you can use either fundamental counting principle or permutations to do these. And again, you pick which one's easy. They mean the same thing. When we're dealing with situations where there's no repetitions, we're doing repetitions tomorrow, it doesn't matter which method you use. So we have 3 girls, which we'll call girl 1, girl 2, girl 3, and 4 boys, boy 1, boy 2, boy 3, boy 4. They're going to be arranged in a row for a photograph. So we want to know in how many ways that can be done if there's no restrictions as to where each person stands. So there's 2 ways we can approach this. We have, in this case here, we have n equals 4, 7. Right? 3 and 4, so 7. And r equals 7. We're taking all 7 students and we're rearranging all 7 of them. So that means 7 pick 7, which we can just use on our calculator, or we can use our calculator for. So 5,040. So that's using a permutation. Or we can use fundamental counting principle. So we have 7 people. So that we're going to arrange. So 7 times 6 times 5 times 4 times 3 times 2 times 1. So multiply those out manually with your finger. That's 5,040. Or 7 factorial. So 3 different ways of answering that question when there's no restrictions whatsoever. You couldn't do the factorial if you weren't taking like arrangements of all of the people. Like if you wanted 4-person arrangements of the 7 people, then this one doesn't work. But both of these do. You just have to have the appropriate number of lines. So part B, the photographer decides that he could take a better photograph if no 2 people of the same gender can sit together. Segregating everybody. That was like at our last staff breakfast that we had. All the girls were at one table and all the boys were at another table. It was like a junior high. Or what was it? Well, the other one that people get. I didn't hear that, and I'm just ignoring that, because the other thing that came up that they said was it was like being a Hutterites policy, where all the guys and girls are separated. I've never been to one, so I don't know. Okay. I'll watch the video tonight. Okay, determine the total number of arrangements that the photographer can make. So some of these you will find it's easier to do fundamental counting principle, right? Because it's kind of automatic. So we got 7 people, and we want to alternate genders. We've got more boys than girls. It's going to go boy, girl, boy, girl, boy, girl, boy. And we had for the boys, there was 4, right? N equals 4. And for the girls, there was 3. N equals 3. So for the boys, there's 4 ways to choose the first one, then 3 to choose the second one, then 2 to choose the third one, then only 1 way left. And for the girls, 3 to choose where the first girl sits, 2 to choose the second, and 1 to choose the last one. So you'd just be multiplying those numbers out. So 4 times 3 times 3 times 2 times 2, the ones that were done. So 144. So that's fundamental counting principle. You can also use factorial notation, because really what you're doing in here is 4 factorial times 3 factorial. There's 4 factorial ways of arranging the boys, 3 factorial ways of arranging the girls. 4 times 3 times 2 is 24 times 6 is 144. Or permutations. So you can use a formula. What ends up happening, because it's so difficult in the graphing calculator, because it's like the menu's hidden, this ends up sometimes being the easiest way to do this. The permutations, like, because this would just be 4 pick 4, right? So we have 4 boys that we're going to pick 4 from, and we've got 3 girls that we're going to pick 3 from. So 4 pick 4 times 3 pick 3, which just amounts to 24 times 6, which is 144. It's the same thing as this, because this you arrive at using this formula, and this you arrive at using that formula. So this becomes, using the formula for permutations is much more efficient if you're dealing with really large numbers, like a really large N or a really large R, where you have to write like a whole bunch of lines out to get to where you want to get to. Any questions so far? Okay. Tanya needs to create a password for a social networking website she registered with. The password can use any digits from 0 to 9 and or any letters of the alphabet. The password is case sensitive, so she can use both lower and uppercase letters. And a password must be at least 5 characters to a maximum of 4 characters. And each character can be used only once. So we want to know how many passwords are possible. So we have 5 characters, so 5 characters, or 6 characters, or 7 characters. And if we remember from yesterday and the day before, or means plus. So whatever we do, we're going to add these together, right, to find out how many total choices she has. We have to figure out what n is. How many different characters there are given what we're told. So digits 0 through 9. Okay, so 0 through 9, so that's 10 choices. Any letters of the alphabet. 26 letters in the alphabet. But case sensitive, so both lower and uppercase letters. So that means times 2. Okay, so that's 54 letters she can choose from, plus the 10 digits, which gives me a total number of digits I can choose of 6. Did I have that right? 52. 52, okay, and then, so 62 is the total. So 62. So for this one, R equals 5, for this one, R equals 6, and for this one, R equals 7. So this would be 62, 62 pick 5, 62 pick 6, 62 pick 7. You could do 62 times 61 times 60 times 59 times 58. That's really what we're doing here. But that starts to become, so it's 62 times 61 times 60 times 59 times 58. This is 62 times 61 times 60 times 59 times 58 times 57. And then the same thing, 62 times 61 times 60 times 59 times 58 times 57 times 56. This starts to be a lot easier to pump in. So you should get, for the 5-digit or 5 characters, 776,520,240 choices. These numbers get big here, right? 4.426 times 10 to the 10. Yeah. 2.4787 times 10 to the 12. And if we add them all together, good gosh, 2,523,690,780,000 passwords she can pick from. Which then you start to see like why the more characters you add to passwords, the harder it is to crack. And I wasn't aware of this until I actually read something recently. I think it was just on Zeit that came up on my, like a thing that comes up on my iPad. Most people now that are pretty savvy with computers and passwords, there's apps you get, and you make up these enormous password strings. It's like 20 characters long. It includes letters, numbers, and it's completely meaningless. But you have this one central app that keeps all your passwords in. You just cut and paste your passwords into your bank and stuff. Because it's like the more characters you get up to, this becomes really hard to crack. Like it would take, like on a normal traditional computer, with like the more characters you have, it would take tens of thousands of years for somebody to crack into it. The problem is if they ever develop a quantum computer, the passwords could be cracked in nanoseconds. It wouldn't take very long at all for the passwords to be cracked. Quantum computer uses quantum bits. It works in I couldn't possibly explain it to you because I didn't barely understand it. It's just a different way a computer has it working that messes with all of the encryption that we've already existed, which is why there's an awful lot of work going on in dealing with new encryption code in case the quantum computers ever working. So try this one. Suppose an online magazine requires each subscriber to have a password with exactly 8 characters. Using the same requirement for the characters described in the example above. So which one's more secure? So this one that was 5 characters or 6 characters or 7 characters, or a single one that's 8 characters? So you're using the same thing. So you're using N of 62 and an R of 8. So just calculate what that 62 pick 8 is and compare it to the 3 added together. Because math is hard. like an enormous number, right? 62 pick 8. 136,325,893,300,000. So the magazine site that she's got, the online magazine site that requires 8 characters, an 8-digit password for those 6 characters, much more secure than this one that takes any of the 3 together. This would just take longer to crack. Okay, Frank, George, Hannah, Iris, Jacob, and Kim have playoff tickets for a hockey game in adjacent seats A3 to A8. 3, 4, 5, 6, 7, 8. Okay, so we got 6 people. Okay. In how many different ways could they sit together in seats A3 to A8? So how many ways can they sit together? So again, different ways that you can do this, right? 6 factorial, which is equal to 6 times 5 times 4 times 3 times 2 times 1, which is equal to 6 pick 6. Okay, so then that is, no, that's not. 1, 2, 3, 4, 5, 6. Because it's going to take it. Yep. No, I knew that was there. So 6 times 5 times 4 times 3. Okay. Yeah, I added it back in. Because I meant to. I left them out when I first did the notes. Okay. Okay, so George and Hannah are dating. So 720 ways. George and Hannah are dating, and how many of the arrangements would they be sitting together? Okay. Okay. So we have 6 spots, right? Okay, so this one's a little bit more challenging. These are getting up to be standard of access questions because they are a little bit more difficult to think about. Because here's what you have to do. You have to think of George and Hannah. Think of them as one person. For now. Okay, so join this again. So we got 5. So that means now we're going to think of them as one person. So that means there's 5 different seats to fill. So 5 times 4 times 3 times 2 times 1, which is 120. But it can be George and Hannah or Hannah and George. Right? So there's 2 factorial ways of arranging this, right? So that, like, if we think of them as one person, but there's 2 ways of arranging them, right? It's George or Hannah, and then whoever's left. So we need to take that 120 and times it by 2 to get 240. Really, we're times it by 2 factorial. If it was a triplet, we do the same thing, right? If there was 3 people, and so let's say it was George, Hannah, and Kim. Then it'd be 4 factorial here times 3 factorial. Just before the game, though, George and Hannah have a disagreement, and they decide not to sit next to each other. Okay? So how many of the arrangements would they be sitting apart? This one is nearly impossible to do, looking at them sitting apart. So what you want to do is take the total number of arrangements. We're going to use what's called indirect reasoning. So indirect reasoning is when you solve a problem backwards or through the back door. You're not actually solving it. Like, this would be direct reasoning because we're looking at what the question says and we're actually coming up with something that directly relates to what it says. This is indirect because we're choosing a backwards way of answering. So what we're going to do to figure out how many ways are sitting apart, we know there's 720 total possible ways they can be arranged, and in 240 of those are sitting together. So the difference between 720 and 240 is how many ways they're sitting apart. Right? So it's the total number of arrangements minus the number of ways they're together. So that becomes 720 minus 240. which is 480. It's kind of like, if you think about really what we want is the complement, right? Staying together is that. We want the complement. So you're finding the complement of part B. And sometimes that can kind of be a bit tough. Okay. Yeah. 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 Okay. When you're doing like the opposite of something, you can ask like because otherwise you have to look at this. You have to add up 5 different possibilities. Okay, that becomes quite hard, right? So this is much easier. And when we start to work with cards, you'll see that that's the same. Okay. Okay, guys. So your assignment for the night. So you're all going to do it loyally while you're sitting here. Page 93 to 94, numbers 5 to 17. Look for the ones that are more challenging to do. Like the ones that are, like a lot of you will probably be able to skip some of the first ones because they're pretty straightforward. So look for the ones that are a little bit more challenging to do.